Hello everyone, welcome to take 3 called I Don't Know Why Technology Won't Work. In this episode you will get a photocopied version of today's notes. So I'm sorry about the quality. If it is a problem, you can take a look at the note picture I posted. So today we're going to do 11.1 real exponents. Remember that an exponent, for example, is if we had x to the third, this piece right here, that's our exponent. A real number is a non-imaginary number. So as long as it's not an imaginary number, it can work for our exponents today. Okay. The first thing we're going to talk about is scientific notation, which is a very common use of exponents. This N up here, this is where we're going to see our exponent. Okay, that'll be some number. And then that A is going to be a number between 1 and less than 10. Okay, so this is our less than symbol. All right. So let's do a scientific notation problem. Number 1 says, at their closest points, Mars and Earth are approximately 7.5 times 10 to the 7th kilometers apart. Write the distance in standard form. So that means without scientific notation. So one way we could write this is that it is 7.5 times 10 sevens. So that's 4, 5, 6, 7. If you put that in your calculator, it's probably going to give you the scientific notation format. So, how else could we write it? Well, how our trick to do it is we take 7.5, and this exponent up here tells us how many decimal places to move it. So we need to move it 7 decimal places. This is a big number, so we need to make it 7 bigger. So we got 1, 2, 3, 4, 5, 6, 7. And then in all these spaces, we add zeros. All right, so that would be our number. And then we could write it out in the format with 6, 1, 2, 3, 4, 5, 6, and we can get our commas in there. So comma, comma, and our units. So 75 million kilometers. All right. Okay, next problem says, how many times farther, so times farther, we're going to be multiplying by something, is the distance Mars Pathfinder traveled, so here's Mars Pathfinder's distance, then the minimum distance between Earth and Mars. So Mars Pathfinder took this long to get to Mars. Hey, how much longer did it go than the other one? So we're going to take the distance from Earth to Mars, and we are going to multiply that by some variable. We'll pick n for fun. So now we got to solve for n. Okay, remember, this is just a big number. You could throw this on your calculator. What I would suggest doing is to do 4.03 divided by 7.5. So that will be 0.54. Okay. When you have these here, you just subtract. So we have 10 to the 8th minus 10 to the 7th will be 8 minus 7. So we'll have 10 to the 1st. Because that's the first, we could easily just move this to, we can move our decimal to get rid of the 10. So We'll move it over 1, which got rid of this part, and our answer will be 5.4. It went 5.4 times longer. All right. So let's talk about some definitions and some information. So exponent definitions. This is some of the stuff. If it's not very clear, feel free to take a look at your notes. But exponent definitions. If n equals 1, we will have b to the n, or b to the 1, or b. So anything to the power of 1 is just itself. Okay? If n is greater than 1, so example, n is 5. Okay? So b to the 5, we would have b times b times b times b 5 times. Okay? If it's b to the n, it's b n times. So however many times that n is. If b equals 0, I don't know why it says does not equal 0. If b equals 0, b to the 0 equals 1. So anything to the 0 power equals 1. And if b is less than 0, okay, we would have a negative number. So negative n sends our b to the bottom of the exponent. We'll look at this a little bit more, but you have done these before. It'll make a little more sense maybe in numbers. Okay, some properties, if you want to take a look at these in your book, they're on page 696. All right, but you've seen these before. So product property, when you have a product property, so a to the m times a to the n, and your bases are the same, you can just add your exponents. Okay, so our bases are the same. We're multiplying, so we can go 16 times 3 plus 7, or 16 to the 10th power. Okay, power of a power, that means you have a power to another power. When you have that, it is the same as multiplying. So a to the m times n. So in our example here, we would have 9 equals 3 times 2, or 9 to the 6th. I'm showing you this step so you know how to do it. If you've got it, then you don't need to show that extra step. Power of a quotient. So when you have a division to a power, it is the same as telling us that we have a to the m over b to the m. So that distributes to both of those pieces. Your b, your bottom number cannot equal 0, then we would have a not possible fraction there. So on this problem, we would have 3 to the 4th over 5 to the 4th. Power of a product. So we have a product multiplication and we have a power out there. What we can do is we can break it apart so that exponent goes to both pieces. Okay, this is an example of when that might be helpful. We have 5x to the 3rd. Well, we can't solve that, but we can do 5 to the 3rd and x to the 3rd and get a number. Okay. And then last is quotient. When you're dividing exponents with the same base, it is the same as subtracting them. So right here we have same bases. We can subtract our exponents. Okay. So a lot of this assignment is going to be working with exponents and reducing that problem, those exponential problems. Okay. All right, examples. using our properties above, find, solve these problems, okay? So we're going to use these exponent rules to solve them. So the first thing I'm going to start with is the top, because they're separate pieces, and then we'll deal with the bottom later. So we're multiplying two exponential pieces. They have the same base. So what I'm going to do is I'm going to add their exponents. Okay. So now we have a division, same base. So now I'm going to subtract their exponents. Right. And last, 2 to the 7th is 128. You could figure that out. You could do the multiplication and figure that out in your head. You could use your calculator, okay? Yeah, you could throw this in your calculator. The point of this, though, is that you understand how to use the rules, okay? All right. Next one, 2/5 to the -1. So what we have here is we have to give that exponent to both of them. All right. Our rule above said that if we had a -1, we need to switch their locations. So now we would have our 5 would go to the top so that it has a positive exponent, and our 2 would go to the bottom so that it has a positive exponent. So that flipping changes their exponents. All right. Page 2. That's page 1. You want page 2. Okay. Page 2. Let's look at these problems now. Okay, now these are with some variables, so we can't just solve them for an answer and throw these in our calculator. So what do we do looking at our rules? How do we solve this? Well, we can give this to the 5th to both of these pieces. So we would have s squared to the 5th times t cubed to the 5th. So that's the same now as just multiplying our exponents. And we would have s to the 2 times 5 is 10, and t to the 3 times 5 is 15, and that would be our final answer. Okay. These steps are to show you to help you get here. More work and a right answer is better than less work and a wrong answer. Okay, if you can skip these steps and get to the right answer, go for it. If not, or if you make a mistake, go back and show your work, and I'm sure you can get the right answer. Okay, so next part, let's solve these. There's nothing we can do on the top, but we can get rid of these double exponents here on the bottom. So what we're going to do is when we have a power to a power, we multiply. So 4 times 3 is 12. Okay. Our y doesn't have another variable or another y, so we can leave y alone, but our x's do, and they have the same base, so we can subtract x to the 3 minus 12, and we will get x to the -9th y. Okay. When we have a negative, that'll send it to the other side of our equation. And now we have nothing else left to do. We're done. Okay. If you're a little confused on these exponent rules, make sure you ask, okay? There's something we're going to be using a lot. All right. Definition of b to a fraction, so the 1 over n. So 1 over n is the same as having an exponent, okay? So a fractional power is the same as not an exponent, I'm sorry. A fractional power is the same as a square root, okay? There's some rules over here. They're kind of confusing. This is what the big deal is. The bottom of that goes inside of the root. If there's a number here, it stays attached to your base. So let's reduce some of these and see what they equal. Trying to keep it on the screen so you can see it. So 125 to the 1/3 is the same as the cubed root of 125, which we know is 5. Another way you could look at this, or you could work backwards and prove this if you wanted to, is that you know that 5 to the 3rd is 25. Multiply that by 3, and that would give you 5 to the 3 over 3, which is 5 to the 1, which equals 5. Okay, so if you need to think about it backwards because it's a number you don't know, something like this will work, right? Okay, B. So one way we can look at this is we could change this to, we could work with it in root form, okay? We know how to do that. What we could do is we could multiply our roots. (14 times 7, which we know is the same as 2 times 7 times 7. So we have those 2 7s in there, which we could take one of them out and say 7 root 2. Okay, let's look at this in fractional form, fractional exponent form, and see if we get the same answer. So I'll have 14 to the 1/2 times 7 to the 1/2. Remember that square root without a number is always a half. Okay, we could rewrite this 14 as 2 times 7. Okay. And we could take 2 to the 1/2 times 7 to the 1/2 times 7 to the 1/2. So we could get the 7 base the same. Now we can add these up. So we would have 2 to the 1/2 times 7 to the 1/2 plus 1/2 is 1. And that would be the same as 7 to the 2nd power. Sorry, to the square root of 2, which is the same. All right, let's try out some more. All right, so to the 4th, the exponent rules still work the same, so we need to just multiply each of these pieces to the 4th power. The question is, though, like this one above, could we break down 81 into something to the 4th power in order to easily get rid of that fraction? Okay. If we think about it really hard, we could figure out that 3 to the 4th equals 81. And that will help us with that fraction. So now I'm going to have 3 to the 4th to the 1/4 times e to the 4th to the 1/4. These fractions are going to cancel out, and I'm going to be left with a 3 to the 1, as well as these. Okay. And our answer it's going to give us is to the absolute value. Why? Well, there's a really important thing from up above. That is just a note for you. So, if we have even exponents, we need to do an absolute value of the variable. Why? Because an even exponent up here multiplied on this e, multiplied by itself, it could potentially get rid of a negative, and that's where our negative would disappear in that answer. Okay. All right. D, last example of this kind before we move on. So let's break this one up into two pieces. So we are going to do the 6th root of 9 times the 6th root of x. We can't necessarily get just a solid answer. But what we can do is we can use those roots as fractions to reduce them, okay? What's funny about this answer is I don't think it necessarily looks cleaner. You'll see what I mean. So we'll change this to 9 to the 1/6. And this to the 1/6. 9 to the 1/6. Well, is there something in 9? Could we rewrite 9 in a way? We could. We could write it as... We can't rewrite it in a way to get rid of the 6 totally, but we can rewrite it in a way that it will get rid of something. Now we can reduce our fractions. So 2 times 1/6 is going to be 2/6. And this will be 3/6. So now let's reduce those. That'll be 1/3. That'll be 1/2. So we can rewrite this as the cubed root of 3 times the square root of x. All right. That doesn't look less complicated, but in our heads, we could do cubed roots and square roots easier than I can do a 6th root. So that's the thought behind it. All right. Rational exponents. So what if you have a rational number, b to the mn? What happens? We kind of briefly talked about this earlier. What happens is we get our root with our n, like we did above, and that top variable needs to stick with your b, okay? Or it can go outside of your parentheses of your b. Okay. A note for you, the nth root of b must be a real number. So this part in here, it must be a real number. It cannot be imaginary. And in this situation, our n is going to be a positive number. It has to be greater than 1. The n itself. If it's negative, it needs to be attached to the n. All right, so let's do this. Okay, why do we do these? Because they help us to solve these complicated fractional problems without our calculator. So we know the bottom goes inside of the exponent. It's going to look something like that. Okay, so the next thing we have to do is think really hard. I guess, okay, let me back up a sec. We could rewrite it like this, but I don't know how to take the 4th root of 625 to the 3rd power. So the other option, what we can do is see if we can work with exponents. So is there a way that we can write 625 in an exponent form that we could maybe get rid of that 4th root, okay? Or to a 4th power. Is anything to the 4th power 625? Okay, well, 5 to the 4th is, Those 4s are going to cross off when you multiply, and we're going to have left 5 to the third power. We know 5 to the third power is 125, and 5 to the third power was way easier for us to do than the 4th root of 625 cubed, okay? So that's what this is trying to have us do. All right, next thing. We have all these crazy exponents going on, but our bases are the same. Yippee. So we can just subtract our exponents. So I'm going to get 16 to the 2/4 or 16 to the 1/2. 1/2 means we're just square rooting 16, which I know, and that is 4. Because we were able to subtract and work with our exponents, we were able to get to that number super easy by stuff we knew without even a calculator. All right, last page. Express this mess using rational exponents. So at the end, it doesn't want any roots. It wants them in exponent form. So let's start with turning this into an exponent and see if we can, how we can reduce it. That's a third root, so it'll go to the 1/3. So by putting that 1/3 out there, we can then make that an exponent for each piece. Okay, so now let's look at all of our pieces. 6 to the 1/3. Does something multiply 4 times by itself to get to 64? Sorry, 3 times, so that would be 4. 9 times a third is just s to the 3rd. 15 times a third will be t to the 5th, and we're done. Okay, so we took this complicated cubed root and we were able to rewrite it in a way that we could solve it on our own. All right, so this one, now we're going to work the other way. Now we want this to go into a radical. Okay, using our we want it to go into one radical. So that means that our bottom number in our fraction must be the same. So what number could we convert these bottoms into? Easiest, simplest. Okay, 2 and 3 most easily go into 6. So what I'm going to do is multiply by each other to make those into a 6. Okay, so if you need a pause, rewatch. 2 times 2 is 4. 3 times 2 is 6. 1 times 3 is 3 over 6. Sweet. So now both of our bottoms are 6ths. So we can turn that into the 6th root of x to the 4th, y to the 3rd. So it's kind of like working backwards and making ourselves a complicated radical. Why? Because it's fun. I think that's why. All right. Simplify. Okay, I'm going to rewrite over this for you because I'm sure you are having a hard time seeing it on here. So that it's the square root of r to the 7th, s to the 25th, t to the 3rd. Okay, so let's rewrite this in fraction form. All of those go to the 1/2 power. Okay. All right, so what I got here is r to the 7/2, s to the 25/2, and t to the 3/2. What we want to do now is simplify those fractions and turn them into, what we're going to do is turn them into mixed numbers so that we can actually take pieces out of that exponent. So what we're going to do here is 7/2 is the same as 3 1/2. 25 halves is the same as 12 and a half. 3 halves is 1 1/2. So what we can say here is we have an r to the third, r to the 1/2, right? We're just going to break apart that fraction for all of these pieces so that we can just easily put that into a root or not. So what I'm going to have left is r to the third out here. I'm going to have s to the 12th and a t. And I'm going to square root that with r s t, because this r, this s, this t all need to go underneath. And now we have a more simplified version. Okay. Because this is the square root, because the root is even, we need to put absolute value over our odd integers because that counteracts each other. All right, last one. Solve. Okay, so let's work to get that x by itself. So I'm going to go -5, -5. 729 equals x to the 3/4. Okay, in order to get rid of a 3/4, we could multiply this by an exponent that is opposite. So I will have to the 4/3. We don't know what the 4/3 is off the top of our mind. So what you can do in your calculators is put it in and see if it's a real number to make sure we don't need to reduce. So you're going to put in 729. You're going to put in a caret and then parentheses 4 divided by 3. And this will get you this number up here. If you plug that into your calculator. If you plug that in, it comes up with the number 665.61, and that's what our x is going to equal there. Okay. So my last note for you, which says down here, if we have an irrational exponent, so 4 to the third is going to be 1.3 repeating, not one we can use. If we have an irrational exponent, you can use your calculator using this caret format. Okay. All right. Homework is page 700, number 21 to 67 odd. A lot of them are going to be just practicing all of these rules. Okay. Let me know if you have any questions and have fun.